Steven Feng, graduate student, and Ed Hovy, research professor, both at Carnegie Mellon University, and Ed is currently on leave working at DARPA, guiding several NLP programs. Welcome both to the Data Exchange podcast.
Hello, nice to be here.
Nice to meet you, Ben.
And so I actually invited the two of you because of an interesting survey paper about data augmentation in NLP. But so we'll start there, but we will also cover kind of NLP more broadly. What are the current challenges and trends in NLP? So first off, I guess very basic for our listeners who are data scientists, data engineers, and people generally interested in machine learning. What is data augmentation, and what is data augmentation specifically for NLP?
Right, so I guess I can answer that question. So data augmentation essentially refers to approaches that can allow you to increase the diversity of your training data without explicitly having to collect a new data yourself, for example, manually through human annotation. And the typical explanation is that this augmented data can act as a regularizer to reduce overfitting when training models, as well as capture desired invariances. So there's several things that kind of make a good or ideal data augmentation technique. Usually there's a trade-off between the ease of implementation and usage versus the performance benefits. And further, the augmented data should usually have a balanced distribution that is neither too similar nor too different to the original data, as the former may result in increased overfitting, and the latter will result in augmented data that is not representative of the given domain at all. So data augmentation has typically been more explored in computer vision through very simple techniques like color jittering, rotation, flipping and cropping images, and so forth, and has slower adaptation for NLP. Now, the main reason for this is likely due to the challenges represented by the discrete nature of language data. This makes it harder to maintain the desired invariances, and in fact, these desired invariances themselves are less obvious for NLP. In vision, you can think it's very simple, like translation invariance, rotation invariance, illumination invariance, and so forth, and they're definitely less obvious for NLP or text. It's also much harder to encode these invariances either directly into the model or used as a lightweight module that you can apply stochastically during training. For NLP, usually you generate the augmented data beforehand and store it offline and kind of load it in during training. And these desired...
Let me ask you too something naive, which is in computer vision, I can believe that there's enough invariance that if you tweak the image, it would look the same. But
Yes.
in text, does it still read like a reasonable piece of text, or is it nonsensical?
Depends on the type of technique you're using and what text you're applying it to, as well as the task at hand. So some works like Easy Data Augmentation or EDA show that techniques like random insertion or deletion of tokens can actually improve text classification performance on many tasks, even though the text itself is more nonsensical and, for example, ungrammatical and so forth. But if you're looking at a task more like language generation, for example, you probably have to be more careful, as feeding in this nonsensical data might lead to the model learning to produce nonsensical text, which is not what you want. So it depends kind of on the task at hand, as well as the technique you're using.
Let me ask you another thing, another buzzy area in machine learning, especially in computer vision. I don't know if this is related to data augmentation. You can tell me if it's not. Self-supervision. So what is the relationship between self-supervision and data augmentation?
So data augmentation has actually been used more recently for self-supervised learning. For example, BART tries...
Let me stop you right there. So for the audience that doesn't know what self-supervised learning is, what is self-supervised learning?
Right. So self-supervised learning is kind of like models that can learn from the data by actually learning to like predict, for example, mass tokens of the data. So it actually learns to basically predict parts of the data itself and as a way to learn. So for example, BERT learns using a masked language model where certain tokens, I believe around 15% of the tokens are masked. And what it learns to do is actually predict these masked tokens themselves. So that's kind of a general gist of self-supervised learning. Not sure if my explanation is very good, but.
So Ed, anything to say about self-supervised learning and data augmentation? Is there any overlap?
Well, actually, I'd like to go back to your previous point, if you don't mind, because I think that, and Steven just touched on it, that hits on some of the fundamental interesting things and shortcomings of data augmentation and the wider question. I mean, it was to be expected that when you have a much more data-hungry procedure like neural network machine learning, you need more data. And it is to be expected that sooner or later you will just run out of data in language and in images and anything you want to do, because in the limit, you have a machine that can remember every single case it's seen, and then it just does a little bit of generalization, and then there you go, right? So if the whole point of machine learning is trying to learn generalizations so you can minimize the amount of training data and still get the result, right? That's the game of machine learning. So then you say, well, can I get a little bit of data to start with, and then just augment it through some little tricks and make it into more, and then I can just pretend that I have a lot of data and I can get the same result, right? That's the game. So then everything depends on when you do this transformation, this data augmentation operation on the data, you want to transform it in such a way, as Steven was saying, that it is sort of true to the original. If you transform every sentence that you got into the same sentence like Joe eats sausages, there's a lot more sentences there, but all the new ones are the same and they have nothing to do with the data. It's stupid, right? You have to make sure that your transformation operation is somehow true to the original. Now, what that true means is actually very difficult. And in the data augmentation literature, what you find is people spend a lot of time developing clever algorithms that replace words, that replace pieces of sentences, that transform sentences, whether they go through machine translation out and back in, whether they take a word and replace it with synonyms, they take a syntactic structure and create the inverse structure, or put a negation in all kinds of things. Those are the algorithms, and in the paper there's a long list of different techniques to do. But the deeper question is, how do you know that when you've run your algorithm, you stay true to the data, you stay in the same kind of space, you don't transform weirdly the data into such a space that you're learning stuff that is completely biased against what you want, right? So the two poles, the two questions here are balance and representativeness. You want to make sure that the things are balanced, that you don't, if your original data set has 90% positives and 10% negatives, not sentences, negation sentences, and your transformed data should also have that, right? It shouldn't change the whole balance. If it is 60% active sentences and 40% passive sentences, your transformed data should also have that.
I was hoping you would say we would write theorems to prove that.
Well, that is where I'd like to help you. This is the interesting part. So this is, Ben, if one could write a theorem like that, if we knew how to characterize what is it that's important in the data, so that we can make sure we maintain that balance. And the second point, representativeness, what is it that was in the data maybe 3 times out of 1 million cases, but those 3 are golden, we need them, right? And if we multiply the data through our automatic techniques 100 times, but we only keep those 3 little ones, their effect vanishes in the noise, right? We must make sure that the representativeness, that all the effects that we want should be there. Otherwise, we bias ourselves in the wrong way. Now, it turns out that the community who's done this data augmentation has done a lot of work on the algorithms, but almost 0 work on the guarantees for balance and representative. And that, to me, is the deeper and more difficult question.
But this is, and we can touch about this later in the conversation, but this is part of the empirical nature of ML and just the way the reward system in ML as well, right? So, exactly. So ML research, right? Quick question for practitioners. the excitement around data augmentation is due to what? Is it because it's producing more robust models, more accurate models, or both, or what? Why are researchers excited about data augmentation from a application perspective?
So
Right.
Steven, yeah.
Right. Yeah, so I think there's a few different reasons. First is that these large language models and neural networks are becoming more popular, which require more amounts of training data in order to train them effectively. There's also been more work on new NLP tasks as well as low research domains. For example, low research languages that require more data. And I think you touched upon it, but data augmentation has led to increasing performance and robustness for several different of these tasks and models. So I think that's kind of the reason why it's becoming more and more popular these days.
Plus, it's also not so hard to do, right? For many effects in language, you can do certain quite simple tricks, as Stephen was saying. I mean, I replace a word. What can you do with a sentence? You replace a word with a synonym, right? You replace the syntactic structure a little bit. You add a negation or a modal. You say could as opposed to should or something. You change the syntactic structure. You don't say Joe went to the store yesterday. You say yesterday Joe went to the store. You translate out into another language and back in again or something. You transform it into a question. There are only so many simple operations you can do. And now you have neural network transformers that can give you lots of ways of making paraphrases and stuff like this. So the field is inviting for someone who doesn't want to do much thinking but wants to do much experimentation. You can just do it and produce it, and you get a lot more data. And as Stephen was saying, you do get a little more generalization, so you get some better results. But soon, I predict, especially as a result of a survey paper like this, you will run out of all kinds of things to do, and you'll say, okay, I can apply all these 27 techniques, but I still don't know if I'm in the true space or I'm not, right? My system does get better, but it still reaches an asymptote. Or it may even get slightly worse, right? It'll get better and better, and then when I do more and more and more stuff, I'll bias myself away, I'll do something, and then I reach an asymptote. So we still get to the same problem, we just delay that problem.
So is there like a PyTorch for data augmentation, like a library that you can just use different kinds of, pick and choose your data augmentation technique? I'm using text. It's like a scikit-learn for data augmentation. Does that exist?
Not yet, but Stephen will make it, right?
I think that's one of the things we're encouraging in our survey paper, which is these unified frameworks and libraries. Yeah. Recently, there have been a couple more that have popped up. I think Ogly from Facebook Research, yeah. Right? Yeah. I think they have like over 100 techniques for like 4 different modalities and so forth. There's also NLP-Aug, which is a lightweight framework for text and audio, as well as things like Text Attack, which is specifically for adversarial examples. Right. So we are seeing more and more of these pop up. Particularly for NLP more recently. So,
but something that kind of just, I guess Ed kind of hinted at it. You can use one of these embeddings maybe, and then replace some words, and then roll your own kind of data augmentation, hacky kind of solution. But in your paper, you folks listed kind of you lay down kind of a taxonomy for this different techniques. So it seems like one way to build this library is just to have one method for each technique to start, and then just build it out slowly, right?
And use the best representative for each technique, and then just make one big package and say, you throw your stuff in, you must make sure that it conforms to the kinds of, that the techniques conform to the kind of transformations you're going to allow, right? If you're working with Shakespearean English, you don't want the transformations to put in words like radio and microwave, right? Because you destroy the Shakespearean English. So you must make sure that the transformations that the machine will do for you keep you inside the space that you're interested in working in. And once you've done that, you run your thing through the package and you get out an augmented, maybe 5 times, maybe 10 times larger data set. And you will get better results. And that'll be great, right? Then the data augmentation problem as such has sort of been closed. It's not that all the techniques have been invented, but there's not an infinitude of techniques, right? And so there will be at some point some kind of closure and we say, okay, this is this part of the field, now we know.
So let's imagine you're giving a talk and I give you 3 slides. Give 3 examples where data augmentation really made a huge difference. You know, like the equivalent in reinforcement will be Atari, AlphaGo. You know, so what are the headline grabbing examples for data augmentation?
Right. So I think the first one you would think of is back translation. So this uses
It's what?
back translation.
Okay.
So what it does is it translates a piece of text to another language and then back to the original language, for example, English. And what you get is kind of a slightly modified or paraphrased version of the original text. And what back translation is extremely popular. It's been used for multiple different tasks and applications, including question answering, summarization, and so forth. So it's kind of a task agnostic, broadly applicable technique that has been used very heavily. So that's definitely one of these I would put on the slides, the 3 slides you're talking about. I guess a second one for me, it would be mix-up inspired techniques, also known as mixed sample data augmentation techniques. So what they do is they interpolate the inputs and or labels of 2 or more examples. So how it's been used for NLP, which does not have continuous inputs because tokens are discrete, is it's been used on the sentence or word embeddings, which are discrete, or for example, mixing higher hidden layers and so forth. This has also shown improvements on multiple tasks. So that's, I guess, a second one. And what I would put on this 3rd slide is kind of these rule-based techniques, which are very easy to compute predetermined transforms. For example, as I stated earlier, EDA, easy data augmentation, which kind of replaces words with synonyms, randomly inserts, deletes, or swaps tokens. And you'd think this is a very simple technique, but somehow it just works very well across multiple different classification tasks. And it's like Ed was saying, you know, this is a very easy to implement and easy to use type of thing. So I guess those are kind of the three major techniques or methods I would touch upon.
Ed, any different examples on your end?
No, I think Stephen hit exactly the right ones. On the last one, I think even the simplest thing, which is just dropping out into the sentence. Before, people were using this for data augmentation already in neural network transformations. People did something they call dropout, right? You train your engine and then you randomly just mask out certain nodes in the interior of the neural network. You just block them, you blank them. And then you thereby enforce a certain robustness in the transformation that the neural network does. It just says, well, I'm not allowed to use this node anymore, but I still want to do the same result. I need to propagate my influence, my sub-combination, my sub-feature combinations around it, so to speak. And you got some kind of generalization which gave some power. So taking sentences and then dropping out individual words or even little preposition phrases or some syntactically sensible unit gives you some of that. And that is the simplest. You think if that's not really even data augmentation, right? It's not even making anything new. It's just, and yet that actually is surprisingly powerful as a generalization technique. So it's things like that that is so nice, so rewarding in NLP. It's not, I don't want to create the impression that this is not good work or anything. It's too simple and therefore to be demeaned. It's actually, it's great if you have a simple technique that really works, right? It's better than a complex technique that really works. And it's an amazing, happy surprise that you can do so much data augmentation through simple techniques and through a set of them like this. So I don't know if there's going to be another paper like this one in, let's say, 5 years' time that is a whole new bunch of data augmentation techniques. I think it will take this taxonomy, grow it a little bit in some places where there's some new sort of sub-variations, but then I think that's done, right?
And then build some of these open source libraries for practitioners, right?
Exactly. Yes. Yeah.
So we can keep talking about data augmentation in this next section, which is more broadly about NLP, where I have a lot of opinions as well.
We want to hear your opinion.
um, but basically, I guess first of all, my pet peeve here is basically, I think, at the risk of dating myself here, but I've been using NLP pre deep learning, right? So, and funny enough, of last year, Ed, I was talking to a graduate student. I'm not gonna name the school, but it was from one of the top schools, right, in NLP, and it's like he was like a fourth year grad student, and he was lamenting that the first year grad students, they only care about deep learning, right? So you know how the old timers in computer vision lament that their conferences are now deep learning, right? So no one really needs to know about computer vision. So this fourth year grad students lamenting that the first year grad students don't even know what PFIDF is anymore, right? So everything is about deep learning. So first of all, we got these large language models, which in my mind, you've got big data, big compute, and then implementation, right? So distributed computing. It seems like the barriers are so high for even you folks who are in a top school like CMU, right? So now you've got to compete with like OpenAI, and I mean, each training run is what, $2 to $8 million, and that's if you do it right? So what are we to do with these large language models? So what's going to happen to the field of NLP in light of the barriers getting higher and higher?
This is a problem that actually various colleagues, when you have a bunch of old-timer professors getting together, this topic always comes up sooner or later. And it hurts the field in two different ways. One is it sucks all the energy and all the new work through the fact that you need large data and large compute, and these things sit in companies, no longer in universities. It sucks all the energy to there. And so that sort of hurts one way, because often they don't publish. Often they just give you the results, and then you say, well, then I sit at DARPA now, right? And the funders, and I actually want to say, let's do this and this. And my boss would say, why should we spend $50 million doing this? Because Google already does it for free, or will do it for free, and it hurts the development of the field inside the universities, in the education. The second way it hurts is it sucks the people, especially it sucks the professors. So a lot of people who would have been professors and would have been happy to be in universities and to train the next generation of students and the next one, they say, no, I can make double my salary at least running an interesting group on this kind of data at Facebook or Google or somewhere. And so I'm just not going to, I'll have some courtesy appointment with the university, but that doesn't mean anything really.
I won't be able to train a model in a university. That's comparable, right?
Right. And so when BERT came out, it was like October or September of that year. I looked at this and I was dead scared. And I called my group together and I said, what are we going to do? There is no way we can compete in the future if we don't have BERT or something like this. So we sat down and we calculated how long would it take, how many machines would I have to buy, and how long would it take for us to build our own BERT. And it turned out to be, if I got some extra money from NSF to buy a whole bunch of servers, and I used at least 12 months full-time these servers, I would have been able to build something like a smallish BERT that we could then use. And then, bless the heavens, Google came and they said, we will make BERT available. And they said this to everybody. It became open. I wrote to them afterwards and I said, thank you for doing this from all the academic people, because if you didn't do this, you would stop all the energy, the academic research energy, because people would say, why must I bother? I can go to Google and do it there in 10 minutes or in 2 hours in my summer, right? Why must I bother here? But the way it's done now, that Google has the benefit, as does everybody else, of harnessing all this power. So we need to somehow create new partnerships between the universities and the big companies for exactly this sort of collaboration, not just data sharing, but also compute sharing and people sharing. So just one more final thought. Many of my students now go for the summer to these large companies and they do an internship. And they used to come back beginning September and say, okay, I finished my thing. Here's my 3-page report. Let's do my thesis. Now, increasingly what happens is they come back and they say, I haven't quite finished. I want to just continue working with them just like 10% of the time. Is that okay? Because I cannot do the work that I want to do here. I can do it there. And they want me to continue because that project is valuable to them. And I say, do they pay you? And they say, yeah, they're actually willing to pay me because they get benefit out of this. And the university, CMU, has now agreed that graduate students, not only faculty, can do sort of like a consultancy for a limited amount of time in a company after an internship, precisely to make this sort of collaboration happen. So what we're seeing is a natural evolution toward a closer connection around the data and the big compute, with the students being the shuttle, for precisely the reason you said. That's a good.
So Steven, why not just go directly to big tech? Why go to PhD program?
Good question. But don't think about it too hard, Steven.
I think a PhD program would be good to, still learn and develop more knowledge and skills, not just on, how to use these large language models, but other areas like linguistics and so forth that we can kind of apply.
But you don't need linguistics. You only need deep learning.
Sure. I mean, yeah, I feel like that's a prevalent thought nowadays, but I think, so these large language models are sufficient for many of the everyday tasks we want, but they're kind of going to reach a plateau or kind of like a limit where like, I think they're going to reach a limit, particularly when it comes to, like common sense reasoning and understanding kind of what humans are able to do or think, or how we're able to talk. Because I think a recent work by Tamer et al. In 2019 actually showed that many of these pre-trained language models, they cannot reason effectively through several common sense tasks that humans are able to do very easily. Kind of demonstrates that there's that gap of logic and understanding of these large language models compared to humans. When you think of how we learn, we kind of learn with less data and using a different process. We don't simply memorize, like word co-occurrences and statistical or pattern information. So I think we need more work on this, like knowledge representation and reasoning, as well as possibly incorporation of structured and linguistically motivated priors, rather than just feeding in tons of data.
So, but then do you need, because right now the way the ML, different areas of ML seem to advance is around benchmarks, right? So then right now the benchmarks in language and computer vision and speech, it's hard to imagine anything but deep learning topping those benchmarks. So maybe what you're describing, maybe the text community should come up with different benchmarks where maybe different models are much more viable somehow. And I don't know what those benchmarks would be though, right? So
I think there's a second consideration also. The benchmarks, you always reach a plateau of any technique. And to break through those plateaus is often not just a better technique or a bigger machine. Mm-hmm. Sometimes you need like a new algorithm, a new method of learning, like deep learning, but sometimes you need an insight. You need the fact that there's extra kinds of knowledge necessary, there's extra intermediate representations necessary, which are too hard to learn without guidance, etc. For instance, if you want to produce a semantic representation from a sentence, you can go and do all kinds of stuff and train a machine. But if you happen to notice that there is a thing called syntax, which is just simple word types and word combinations, and you train for that as the first step, and then as the second step out of that, you get the semantics, you can reduce by a great factor the amount of training data you need, because this middle level of constrained vocabulary, which we call syntax, it guides you to the right kinds of structures and combinations. So it's a big savings in the amount of data you need to get the same result. Now, so when you get to the end, when you start reaching an asymptote in any kind of benchmark, and somebody walks in and says, if only because people can do this and people say that they think this and this and this thought at the same time, if only we could do that generalization that people do and bring that in, then we will be able to get so much further. And I've managed to do it, and look what I've done. If somebody can show you that tomorrow, everybody will say, well, let's learn that new extra piece of magic knowledge, right? That happens. And I believe that's going to happen in the future too. And I believe that happens at universities more than in companies, precisely because universities are more resource constrained.
Yes. Yeah. So the question is, how many people are working on these other approaches, right? Because it seems like if you think of ML, Steven, it's like a search problem in the space of algorithms. Everyone is searching over here in the space of deep learning. And so these other techniques, at least in NLP and computer vision speech, may be not as there may not be as many eyeballs and people working on them, right?
I think one area that has seen increasing interest, which I think is very good, is multimodality.
Yep.
The fact that you're able to incorporate information and create representations from multiple mediums. For example,
but each mode is
video.
using deep learning, right?
That's true. I do think, though, that the multimodality is a step closer to how humans learn. We associate words with things we can see, things we can touch, things we can feel, and so forth. I think there's still that difficulty there with abstract concepts that don't have physical representations. So humans, even with abstract concepts or non-physical entities, kind of still able to make these mental connections that machines have difficulty with.
Ed is right. If someone can show some real marked improvement using a different approach, then people will go there. It's just that I've been waiting for that for the last several years.
You'll notice that the approach need not be an algorithm, right? So I believe that neural network is a way of information transformation. In fact, I think image interpretation and language interpretation is a matter of notation transformation. You transform a speech wave into a text string into a parse tree, a long text into a short text, a big set of knowledge into one document. It's just transforming the notation, right? So before machine learning, before the 1990s, people wrote rules. And they had rule-based parsers and expert systems, and they had rules to do the transformation to go from input to output. Then came machine learning from the speech community into machine translation and then into NLP proper, starting in 1989 to about 1996. And then everybody used machine learning techniques to do the transformations. They learned them rather than wrote them. Now comes neural networks in 2013, and it says, I don't even have to create the representation so much. I can start with these trained embeddings and things, and I can do something. I now learn the transformations and the representations together. But it doesn't take away the fact that there is a transformation and that the technique is right. It's a generic technique that you apply. What you still need to do is understand what is the problem, what's the input and output, what is the representation you need. Am I looking at part of speech labels, semantic role tags, image labels or something? What is it that I want the machine to do? What's the vocabulary of output symbols, the representation language that I give in and out, and I must transform through? That design is not what a machine does, that we do. And we make the work interpretable to us. And it's the limit of our own creativity to say, am I going to have a machine look at a movie and tell me the plot and tell me the goals of the person and tell me, am I have a machine look at a whole bunch of things and tell me here's all the different perspectives of it and this is this information and not, right? At the moment, we don't think those thoughts, but soon when our transformation engines are good enough, we will start thinking, how can I take those complex things, formalize them down, and train my machine?
By the way, there's also, because the language models are getting larger and larger, more expensive to train, there's also the energy and environmental costs, right? So Ed, you're sitting at DARPA. Are you seeing proposals that give you hope for more efficient ways of doing things, especially in the language realm?
Yes, there's a new program being discussed called Learning with Less Labels, LWL, that is exactly along the lines that we're talking about today. The whole goal is to scale up a problem 100-fold with less and less and less data, and to say, I'm going to give you the same question, but not translating between two languages, but translating between 20 languages and 200 languages with less and less data. That sort of challenge, right?
So motivating researchers, really. It's a way to motivate researchers to work on this problem.
The goal of DARPA is twofold. One fold is to say, what is a deep problem that is not going to be solved by just people doing little things as they do before? And then DARPA points to the fact that the internet would not have happened, that machine translation would not have happened, that geospatial, would not have happened,
or the autonomous vehicles, the progress, right?
Would not have happened, and so on. DARPA comes and looks for big problems and infuses. So my job at DARPA, and people like me, our job is to say, in the little field that I work in, what is a problem that is deep and important for society and for the military, but for society, that is not a small thing, that a little step that people in ACL world and stuff are going to solve just by the normal creation of a little data set of things, and then they're just going to extend out and do it. What is a big step that I can put $50 million or $80 million over 4 or 5 years, that 20 teams can work on this all around the country, the best teams, and can crack it open and can do it. So one example is, when you go to a restaurant, you sit down and the menu is coming, and you will order the food, and eventually you will pay. Now, nobody told you this. You sat down in a restaurant 20 times and then you figured it out, right? You learned that. Can you build a machine that can read 1 million texts and can build these little event sequences for everything, anything that's in that text, whether it's restaurants or illnesses or COVID or anything like this, and can remember them in a big script schema library? And so when it reads a new story, it says, and you stop it halfway, you say, okay, I'm giving you a story over 6 weeks, but I'm stopping at week number 3. Tell me what's going to happen. You as a human, you will say, oh, I know about epidemics, I know about earthquakes, I know about restaurants, I know about election campaigns, and you will predict. No machine can do that today. So one of the programs that I'm managing now with about 12 teams around the country is to do exactly this, to read 1 million documents in 3 languages with images, and to learn these schemas, and then to be able to predict, and we measure how good is your prediction. So we're not going to solve the problem, but by putting this knowledge out there and having the teams go 5 years later, most of ACL will know about this, and there will be workshops and tracks on this. So DARPA has a history of injecting these kinds of problems into the community, and then the techniques come. All the techniques come and all this stuff, but that initial core problem, that's the hard part. That's
so Steven, let's wind this down. So anything in NLP and ML that particularly intrigues you, that you're excited about over the next few years?
Right. So for me, kind of an area of focus I've been working on more recently is text generation. So I can touch upon some things that I find might be intriguing here. So the first is controllability. So you see these large language models like GPT-2 and GPT-3 can generate very fluent and natural text. So one area people are focusing more on is the ability to manipulate the output text with respect to certain qualitative properties. So, the sentiment or style, particular words that should appear in the output, and so forth. And I think this is a good step towards more effective text generation in general, because I think good text generation is not just generating fluent text. It requires you to master, the style, content, context, and situation, and so forth. Because, we as humans, we don't just simply spout out stuff. What we say is determined by, who we're talking to, state of the conversation, the context and surroundings, and so forth. And controllable text generation kind of allows for some of these factors to be kind of constrained or manipulated as appropriate. So specifically,
Stephen, is this related to what some people call, and this is a funny title, the prompt engineer? You know, these are the people who are masters of interacting with GPT-3. They can get, like you and I, the three of us can interact with GPT-3, and then it wouldn't come up with anything clever. But these master prompters, prompt engineers, supposedly can. So this is much more of a systematic, principled way of interacting with these systems, then, right?
yes, exactly.
It's the science behind the prompt engineer.
Right.
And
I
that's
think
a university thing. That's not a company. Right.
Yeah, I think controllability. There's a lot of things to investigate here, like improved disentanglement. Like, can we better separate syntax from semantics for improved controllability? More unsupervised approaches for controlled text generation as well, and as well as the ability to control.
Is reinforcement learning a thing in NLP?
So I think it's been used certainly for NLP, but I'd like to see more of it as well.
More practical? Are there real practical, or is it more researchy? You know what I mean?
I think it's.
Is it at the point where people are actually using it in systems that are out there?
I don't think quite yet. I mean, it's a fairly new thing in NLP, but you see a lot of it. You see a lot of discussion about it.
I see.
Sorry, go ahead, Steve.
Right. Yeah, I think reinforcement learning, active learning, and human-in-the-loop learning be good things to incorporate more into our NLP systems. Specifically, we want systems that can kind of learn and improve on their own, kind of like humans, how we learn and improve. If we do something wrong, we know not to do it again, or how to do it properly the next time. I think that's something that is lacking a bit more in the NLP space.
So Ed, one of the things that I'm hearing more and more about, and it's somewhat related to NLP, I think, knowledge graphs. Is that something worth paying attention to again? Because it was hot back in the day, but now it seems to be back again.
There's different people mean different things when they say knowledge graphs. So some people think any little triple store connected together is a knowledge graph, and of course that's not really a responsible knowledge graph. You can show easily that it just misses information. It's just not a good way of doing things. But if you take any traditional propositional model, a logic propositional model of symbols that are related by relations and properties and things, that is also a knowledge graph. You can transform that into a knowledge graph, and that is a responsible way of representing knowledge in the symbolic space. Now, when you come to neural network land, some people say you don't need that anymore. Everything is an embedding, and it's not interpretable. It's in your embedding plus transformer plus your machine, and all you need to do is be able to access it and ask questions and it'll tell you what it knows. So the knowledge graph has been absorbed into this machine and is no longer accessible to people so you can look at it. Other people say, no, the role of the neural network information transformer is to build such a thing, and this output is the knowledge graph, a good knowledge graph, which you can then manipulate in other ways, in symbolic ways. How that will play out is unknown today. It's unclear whether what the AI people used in the 70s to call the procedural versus the declarative tension. Do I declare things and make big complex representations and simple rules for inference? Or do I put everything in my rules, make big heavy rules and very simple small representations? The neural networks say we put everything in the rule engine, like the transformer. It's all in there. There is no more representation, it's all hidden. And the traditional guys say, no, I want all my stuff, and I just want the little transformer engines to be a neural network. I expect we'll see both, but I don't know how it's going to play out. That's one of the most interesting questions for our field, for AI in general, for the next 10 years to figure out.
So let's close by speculating a little bit, I guess, more near term, next 1 to 2 years. on what will happen to these large language models. So last year I had Neil Thompson, who's an economist working at CSAIL in MIT, and they had a paper out on the computational limits of deep learning. Basically, we're running out of compute. So GPT-3, 175 billion parameters. I think Google hinted that they had something that had a trillion parameters, maybe, right? So next 1 to 2 years, will these big tech companies keep chasing larger and larger models, or is that even they are hitting a wall? I guess that's kind of my question, because basically, even for them, I think at some point it becomes too expensive, right? So what will happen, I guess, with these large language models in the next over the next year? I guess we'll probably see another generation of bigger, and then what point does it diminishing returns, right? So,
I think what you said about the limitations of the hardware and the energy becomes an issue too, right?
even for them, right? Even for
Yeah,
them.
even for them. So it's, in some sense, you can say a language model is just a sort of episodic memory. It's a memory of everything the thing has seen, right? It's just a big language model, and with a little bit of generalization kind of added, a sort of generalization of word parts or word part combinations. It's nothing magic. So there's certain things that just you cannot imagine how it would be able to do unless it had infinitely many examples. It just deep reasoning, understanding logical reasoning and modus ponens and all kinds of things. Unless you really train the model to do things step by step, just one big language model, one big brain is not going to do it. So you can say you can learn as big a language model as you want, and then you still end up not being able to get to what you need. And here's a simple example, and then I'll stop. If you look at, I went recently to look at GPT-3 to say, can it add 2 digits? So I had a student, I asked him, can you make the smallest neural network, the smallest 2 nodes, 3 nodes that can add 2 digits? And he made a little thing, and it added, it said 1 plus 1 and 3 plus 2 and 4 plus 9, and it came up with the right results out of about 7 or 8 nodes in 2 layers. And when we looked to try to figure out what was going on, we couldn't. There was no pattern we could see how the numbers were computed. When he then took 2-digit numbers, 17 plus 19, 14 plus 13, etc., or when he took the sum of 1 plus 6 plus 9, 3 plus 4 plus 2, etc., he kept on growing this, and eventually we discovered that the machine, it had to grow a little bit in number of nodes, but eventually it invented an accumulator node, a running total. It was cheaper for a machine to say, I'm just going to look at the first 2 digits of what you give me and create their total, and then sum the third one into that total, than to try to remember all possible sums of 3 numbers. So it made that switch itself to try to invent an accumulator by just seeing what was cheaper. So that is a surprise. Then they're just doing some creative thinking as opposed to just some blind generalization, right? That sort of creative thinking seems to me not very frequent, and a very difficult thing to see how it would do for more complex. So I went to GPT-3. Now I tried to find out, can it add 2-digit numbers? Can it add 3-digit numbers? Can it multiply? Can it multiply 2-digit numbers with one another, 10 times 49, etc.? And I looked at I found a paper that showed graphs of what it can do and at which point it stops. And then I went to the web, to Google, and I said, well, can I find online things like little children's multiplication tables, 6 times 9, these tables you put on where the kids learn and stuff like this. And for those places where you could find those tables, GPT-3 knew them. It knew how to multiply because it had read those tables. For when you have 3 or 4 or 6-digit multiplication, it fails. It doesn't know how to do that. Now you can give it 17 times more power. I don't think it's ever going to know how to do that. I don't see how, because it doesn't have the training data, right? It's not a thing it knows to train about. So it's not a matter of just growing bigger. It's a matter of us growing smarter in telling it what we want it to do. That means we must make representations and guide it and teach it. That's where our energy has to be. So I think blind growing bigger is, sure, I can do it. It's not so meaningful. It's the intelligence in saying to guide it to intelligent intelligence inside. That's where we must think how.
So, Stephen, let me close and tweak the question for you. Instead of large language models, in terms of embeddings. So I'm a user of these embeddings. There's so many embeddings. In the library I use, it's not even listed in one screen. You have to paginate. There's so many options, right? So what will happen to these embeddings? I mean, for the user, it's just, pick whatever. There's no guidance, right? So is it? Are we at the point where these embeddings are good enough for most tasks? Because basically, they're just basically building blocks, right, in an NLP pipeline. So maybe we have enough embeddings to carry us for the next 10 years. So what's your take on embeddings? What will happen there?
So I think, yeah, like you said, embeddings are kind of like the building block.
Yeah.
One thing I was curious is, can we learn these embeddings in smarter ways? So currently, you have pre-trained embeddings like Word2Vec, which kind of uses like word occurrence information.
Right.
You have contextualized embeddings, which are the next step higher, I guess, in terms of quote unquote intelligence. They change depending on the surrounding words or context. So I'm curious,
You even have sentence embeddings, right?
Right, exactly. Like, what's the next step on top of that? Can we possibly inject more information into these that are more than just the context and the word co-occurrence information? So I don't have any clear thoughts. A couple of areas I would like to see more is maybe injecting some more structural information, especially when you have longer pieces of text like documents. Like humans, when we are thinking or writing, we have this roadmap or plan of the entire piece of text. We think of it as like an intertwined passage rather than separate disjoint sentences. And these document level phenomena are currently like not considered very heavily when it comes to, thinking about invariances for data augmentation or templates to guide, text generation or document level tasks such as summarization. So I think that's one thing that I would hopefully we'll see more of. The other thing, just to close off, I guess, would be the current sampling and decoding process for text generation. It's kind of based heavily on assumptions or constrained with regards to the probability distribution of the tokens. For example, it assumes like a Zipfian distribution or follows strict probability patterns. Kind of lacks the framework to learn the full complexity of human preference variation. So if you think about like the language model inside us as humans, it's much more complicated. We don't simply sample tokens by probability, right? So maybe there's smarter ways we can attempt to learn this more general or human-like preference function for sampling text or tokens, which will hopefully result in more natural, flexible, and human-like generation. So those are just some of the thoughts that I've been thinking about more recently with regards to text generation and NLP models.
And with that, thank you both. This has been a great and very illuminating discussion.
Thank you, Ben, for inviting us.
All right.
And before we close, I'd like to say, please check out our survey paper and archive, as well as our GitHub repository, which we will keep constantly updated with the newest data augmentation work.
I will definitely link to both of those.
Yeah.
All right.
And I'd like to say thanks to my co-authors, especially Varun and Jason, who helped out a lot. And of course, thanks a lot to Ed Hovy for his guidance and advice, and to you, Ben, for giving us this opportunity to have this insightful discussion.